So we've seen that all open covers are fundamental, and this is very useful. But how about closed covers? Well, we could ask even for arbitrary covers, but that would be even more ambitious. Well, in one sense, very obviously not, right? So R is going to be the union. Let's look at all x in R of x. And a single point x in as a subset of R is closed, because its complement is these two rays, which is a union of open intervals, or you could think in the metric sense. So real numbers are certainly not, so it's a union of closed sets, and so this would mean, so, and clearly every set. So what are our counterexamples? Basically anything that's not open. So for any V in R contained in R, V intersection X is X or it's empty, so open in X. Yeah, so the only case where you could have, every point being a fundamental cover is going to be for the discrete topology, which R certainly does not have. And so we have non-continuous functions on R. Okay, so this was too much to ask for. But our first proposition, this would be important enough, but we'll not call it a theorem yet, because we'll strengthen this better. So this was the problem, was we had too many of them. And when we looked at open sets, we used the fact that arbitrary unions of open sets is open, when we showed that open sets form a fundamental cover. And arbitrary unions of closed sets are anything at all. So that's the problem here. Okay, so you can guess from what I just said that if any finite cover of a space X by closed sets, and for finite ones, let's enumerate them, F1, Fn is a fundamental cover. Okay, so this gets us somewhere, and this is already very useful. We'll want to sharpen this a lot. But first, let's prove this. Okay, so let V be contained in X, and suppose what we know from this is, suppose we know that V intersection Fi is open for all I. 1 is less than or equal to I is less than or equal to N. Well, these are closed sets, so as you would guess, you would want to deal with them instead by looking at closed sets intersecting with Fi. Okay, so then if I look at instead the complements, so then what we know is this is open for all I in Fi, of course. Okay, then if I look at V, not V, Fi. Then Fi, the complement in Fi of V intersection Fi sorry about that. That's a V intersection Fi. So this is closed in Fi for all I. Okay. Hence, well, closed subset of a closed subset is closed. So hence in X. So all these are closed, not just in V, Fi, but in X. But what are these? These are points in V which are not in X. So this is also the same as looking at the complement of V. So X minus V intersection Fi. So those points in Fi which are in the complement of V. It's exactly the same thing, since Fi is a subset. Okay. So therefore, X minus V now is going to be, this is a cover. So it's union I equals 1 to N, but this is a finite union of X minus V intersection Fi. So given a cover, any set is the union of its intersections with members of the cover. So this is closed in X. Therefore, V is open in X. So if we had a finite collection of closed sets, then we could flip things around and look at complements, and then use the fact that closed sets of closed sets are closed. And in the outer space. So to conclude that V is open. Okay, but crucially, when for a single set we use closed sets of closed sets, but to put it together, we needed open set. We needed to take only a finite union, so it doesn't work for an arbitrary union. So we want to improve on this, and the way we improve on this, well, we clearly need some hypothesis. We look at locally finite covers, because the limitation of finite covers is that for a set like R, it may not be natural. We may want to have bounded small intervals which cover it. With R, you'll need infinitely many. What you make sure is near any point there are only finitely many. Okay, so a cover F alpha, I'm writing it as if it was by closed sets, and it will be in our theorem, but the definition of locally finite doesn't depend on them being closed. So this is locally finite if for all x in X. So I have assumed I've fixed f(x) x. There exists an open neighborhood, W open, with x in W, such that the set of all W intersection F alpha is empty, or let me write it in a more formal way. So if I look at the set cardinality of the set of all alpha in A such that W intersection F alpha is non-empty, this is finite. Okay, or maybe, yeah. So the number of sets, so I need not even have set cardinality. So those indices, the number of sets that intersect a particular open set, not necessarily any open set, but given any point, there's an open set, I'll call it W sub x, open, with containing x, so that only finitely many of the closed sets cover this part, and the others are far away from it. Okay, so this, we'll see many local properties. Normally you have to be a little more subtle. What you need is, given an open set, there's a smaller open set inside that, but for finiteness, properties kind of inherited. Some subset, if you're smaller than finite, you're automatically finite. So that subtlety which we'll see in local connectivity, for example, goes away here. But so locally finite means that they may be infinitely many, but intersecting any, given any point, we can find an open set containing it, so only finitely many open intersected. So now Wx form an open, okay, hence fundamental cover of X. Okay, so thus let's just record V contained in X is open if and only if V intersection Wx is open for all x in X. Typically you don't need to take so many open sets, you just need to take a sub collection of these, but for our formal proof that makes no difference. Okay, so for all x, if we have V intersection Wx is open, then we know V it's open, just because Wx form an open cover. They're an open cover because they're all open, and Wx contains X, so their union is everything. Okay, so now we have things put together nicely. So theorem, a locally finite cover F alpha, alpha in A is by closed sets. Sets is fundamental. Okay, let's prove this. So suppose V is in X is such that V intersection F alpha is open in F alpha for all alpha in A. We want to say V is open. Okay, so we know V is open if and only if V intersection Wx is open for all x in X. Okay, so we have to show that, so fix x in X. Okay, well, we show V intersection Wx is open. Okay. So now, if I look at F alpha intersection Wx, so if I look at this collection, alpha in A naught is a finite AX, let's call it, index closed set, finite closed cover of Wx, where Ax, you may guess, is the set of alpha in A, W intersection F alpha is non-empty. So most of the closed sets, all but finitely many, just don't intersect W alpha X. So if you look at so these are relatively closed, and there are only finitely many which are non-empty. So this forms a finite closed cover, so hence a fundamental cover. So we know finite closed cover. Now what we know is V intersection F alpha open in F alpha implies, again we use two-step inheritance of subspace topology is the same as one-step inheritance here, one of the basic properties we proved. This implies that V intersection F alpha intersection, sorry, I will rather write it the other way. We want to show V intersection Wx is open. So this implies that V intersection Wx intersection F alpha is open in Wx intersection F alpha for all alpha in fact A, but in the smallest set X. But then this is a fundamental system, right? So F alphas are a fundamental system. Okay, so V intersection, yeah, perhaps I should have written, well, okay. So this I should really write as V intersection Wx intersection Wx intersection W alpha to get things exactly correct. Let's as well write it that way. The two Wx's make no difference, but they let you align correctly with the hypothesis. So if I look at Wx, it has a closed finite cover by sets of the form Wx intersection F alpha, where I only look at those alphas where this is non-empty. And what we know is V intersection F alpha is open in F alpha. So the double subspace topology will tell you that V intersection Wx intersection F alpha is open in Wx intersection F alpha, that is by further intersecting with Wx. And that can be viewed in this way, that V intersection Wx intersection each of these fundamental closed sets is open, and so that implies that V intersection Wx is open. So in Wx or in W or in X are equivalent because Wx is open here, just to clarify there. So this implies V intersection Wx is open in Wx, hence in Wx is open, so hence in X. Okay. So what we know is V intersection Wx is open in Wx, and so V, which is the union of these, is open. Okay. So what we have proved, and let me just recap the proof. Locally finite cover by closed sets is fundamental. Point is, I take a set V whose intersection with each of these F alphas is open in the F alpha. So it's relatively open. It's open in the subspace topology on F alpha. These are too many, so I can't simply take the union even after taking the complement. But instead, I note that to show V is open, I just have to show its intersection with this open cover. Wx is open. And so when I further intersect V intersection alpha, F alpha with each Wx, now because all but finitely many are empty and can be thrown away, I get a finite collection of closed sets in Wx, closed with respect to subspace topology of Wx, which cover Wx and hence form a fundamental cover of Wx. So we can conclude V intersection Wx is open because V intersection each of these F alphas is open, and this is a further intersection of closed sets. Okay. So putting these together, we see that a locally finite cover by closed sets is fundamental, which is to be put together with the previous theorem, which says that given a locally finite cover by closed sets and functions on each of these which are consistent, you get a continuous function on the whole set. This is the crucial result that turns out to be quite very useful even when one gets to algebraic topology and so on, when you're or CW complexes, handle bodies, anything in real life when you're dealing with topology.